Hello everybody, welcome to this second lecture of the course PHIL110. Today we're going to be talking about the second pillar of logic, and then we're going to start getting our feet wet a little bit just by looking at basic terminology that we need in order to articulate logical principles. So last time we saw that logic as a discipline has a dual nature. It's both an art and a science. And we talked a little bit about the significance of what it means for logic to be an art, leaving aside what the science part for today. So just as a reminder, when we say that logic is an art, what we're asking is a practical question, not a question of skill. And that question is, how should I reason if I am to do so correctly? And the answer is going to be given in terms of a collection of techniques and patterns of reasoning, or should I say, good patterns of reasoning. And those are the things we're going to be learning this semester. On the other hand, science is also an art, and science, sorry. And when we say that logic is a science, then we are asking a theoretical question, not a practical question. And that theoretical question is, well, why are the prescribed techniques and patterns invariably correct? That is to say, they will never, ever fail us. They will never lead us to the wrong answer. And this is indeed a theoretical question that makes logic a science. So let's have just a little bit of a historical snippet of how logic has developed through the ages as a science. Now, Aristotle, you might have heard of him. Aristotle was a Greek who was the teacher of Alexander the Great, perhaps the greatest general in the history of the world. But he was primarily a philosopher, and he was the inventor of logic, both as an art and as a science. Aristotle was also the inventor of many other disciplines that we practice today, like physics and biology. Also one of the most famous ethicists of all times. And he was also the first historian of philosophy. So Aristotle was an amazing, amazing mind. And if you want to know more about how someone could come to the idea of inventing logic, I'm going to be teaching a graduate seminar in the summer on that topic. So that should be quite interesting. But for today, I'll just mention a few very basic things. So when we say that Aristotle is the inventor or the father of logic as an art, that means that he gave us a set of fundamental techniques and patterns of correct reasoning, and those are known as syllogisms. So in this course, we are also going to study syllogisms, but in the second half of the course, we're going to start with something else. Because things have evolved and changed, of course, over time. Aristotle did his work 2,200 years ago, so one would expect that maybe we can do it a little bit better. In fact, we're going to start with something called statement logic, which was developed in the century after Aristotle by a group of philosophers known as the Stoic. But that's for another day. Aristotle was also the father of logic as a science, because not only did he give us a set of correct patterns to follow if we are to reason well, but he also gave us the tools to explain that those rules were indeed correct. That is to say, the tools to explain why they always work without exception, and that It's not just that we haven't seen exceptions yet and we hope that it continue. No, it's a much stronger type of explanation in terms of there being no possibility of ever encountering an exception. And this is the object of logic as a science. Well, as I said, we're going to do both in this course, the elementary parts of both. Now, what I would like to talk about now, since we're going to look at the syllogisms later, is two very important methodological discovery. That is to say, general maxims about how we can analyze problems. And it was essential for Aristotle to develop to come up with those two discoveries in order to be able to invent logic as a discipline. Now, for the first one, let's just start with an example. That's a super famous example. That might be the one that is written the most often in logic textbooks, at least logic textbooks used in philosophy. So the argument has two premises that are listed above a horizontal line, and then the conclusion is written under the horizontal line. So the horizontal line means something like it's therefore, right? So we have two starting points, two premises, and it's all animals are mortal, and the second is all humans are animals. And then the conclusion is therefore, right? All humans are mortal. And the basic question we want to ask ourselves is, well, does the conclusion follow from the premises? That is to say, if the premises are true, and we don't know whether they are or not. I mean, they do look true in this particular case, but more generally, it doesn't matter so much whether the premises are true here. What we want to ask is, if they are true, is it also required that the conclusion is true? And we want it to be not just required most of the times or if things go well. No, we want it to be necessarily the case. Right? So we want to try to understand how we can answer that particular question in general. We're going to do it first with respect to that example, but then we're going to generalize what we learned from it. And intuitively, it seems that the answer is yes. Yes, the conclusion does follow necessarily from the premises. And when we answer yes to that question, then we say that the conclusion is a logical consequence of the premises. So that relation of logical consequence is really what we are trying to understand when we study the science of logic. Now, I said intuitively the answer is yes, but why is it so? How can we explain that this is the correct answer? Now, the first question we might want to ask here is, well, perhaps the conclusion necessarily follows from the premises because of the meaning of the terms animals, humans, and mortal, and perhaps even specific facts about animals and facts about humans and facts about mortality or things like that. Is it because of that that the conclusion follows from the premises? Well, let's look at it again, right? It seems that it's more about the pattern that the words animal, mortal, and humans do. Basically, we could replace the words animals, mortals, and human, and it seems like it would still work, right? The conclusion would still follow from the premises. So that would suggest that the reason why the conclusion necessarily follows from the premises has nothing to do with animals and humans and mortality and things like that. It's really just about the patterns in which those words are occurring in the premises and the conclusion. And one way of making that very clear is to remove the three terms and to replace them instead by variables or placeholders, if you prefer. And in fact, Aristotle was the first to introduce variables in order to see those general patterns of logical reasoning. So that was a very important and significant advance, even if now we kind of take it for granted because we learn algebra from a very early age. But now let's look at this pattern where I have the x's in, where I have the x's in orange, the y's in red, and the z or z, we're in Canada, z in blue, just to help see that there's a pattern here. And it seems like we could replace x, y, and z everywhere by three other words, and the conclusion of the resulting argument would still follow from the premises. So this is why the use of variables is very important in logic, just like it is in mathematics. It enables us to develop a very general point of view that applies to many cases. Okay, so we can perhaps put a label on this first thought of Aristotle, which is topic neutrality. The idea is that since what makes this argument good has nothing to do with humans and animals and mortality, it's really about the pattern, the topic of the argument is absolutely unimportant. It's just that pattern that is important. And so we can say that logic is topic neutral, and by that we mean that their rules, the rules of logic, can be expressed with variables, and that reflect that the topic, what we are actually talking about, doesn't matter whatsoever, and that all arguments fitting that pattern will be good or bad, depending. So let's do a little bit of an exercise to think about that a bit more. So here I'm going to give you premises, and I'm going to ask you to think about what conclusion would necessarily follow from those premises. And then we're going to think about why that seems like the correct answer. Okay, so here's the first case. And hopefully you don't know much about islands of Spain, but let's just go with it. So first example, the Canary Islands are in Spain. Spain is in Europe, so what necessarily follows? Think about it for a second. Yeah, what necessarily follows is that the Canary Islands are in Europe, right? That one is easy, isn't it? Because the pattern is exactly the same as our pattern for humans and animals and mortals. Now let's use a slightly different pattern. The Canary Islands are larger than the Caribbean islands. Who knows if it's true? But it doesn't matter. The Caribbean islands are larger than the Tristan da Cunha Islands. Again, no idea. But then what follows necessarily from those two sentences? Right? We're not saying those two sentences are true, but if they were true, what would necessarily follow from them? Well, it seems that what would necessarily follow from them is that the Canary Islands are larger than the Tristan da Cunha Islands, right? Now, suppose I tell you that the first premise is false. Does that change your mind about the fact that the Canary Islands are larger than the Tristan da Cunha Islands necessarily follows from those two premises? It shouldn't, right? Because the question we're asking is really about the connection between the two premises and the conclusion in virtue of what they mean, and not so much about whether the premises are true. That's a different question. Right? So learning that the first premise is false shouldn't change your mind. Okay. What about if you know something about the Tristan da Cunha Islands? There are fun facts about this island if you want to Google it. But do you need to know anything really about the Tristan da Cunha Island in order to know that the conclusion that necessarily follows is the Canary Islands are larger than the Tristan da Cunha Islands? No, right? So the knowledge which is specific to those three islands is irrelevant because logic is about studying a logical connection which is topic neutral. So it should not. Now, one thing that might very well matter though is really understanding the meaning of the phrase is larger than and its logical properties, perhaps. So we need to know a few facts about the proper meaning of the phrase is larger than in order to make the correct inference to the conclusion. Okay, we're going to actually study a lot of properties of relations later on in the course, but for now I'm just flagging that this is important. Now here's another example. The Canary Islands are larger than the Hawaii Islands. The Hawaii Islands are the largest islands good for a winter vacation, and we might need it now given that we're buried in snow. Therefore, now I'm giving you the conclusion, the Canary Islands are not good for a winter vacation. And then we ask ourselves again, does the conclusion follow from the premises? And does it follow necessarily from the premises? Take a second and think about that. Well, the first says that the Canary Islands are larger than the Hawaii Islands, and that the Hawaii Islands are the largest islands good for a winter vacation. That means that the only other islands that are good for a winter vacation will have to be smaller than the Hawaii Islands. Right? But the Canary Islands are larger, so it must follow that they're not good for a winter vacation. Right? But now, again, we need to know a number of facts about the meaning of the phrase is larger than. Right? That's really important, just like for the previous example. But we don't need to know facts really about the Canary Islands, the Hawaii Islands, or which islands are in fact good for a winter vacation. It's just about the connection between the ideas in the premises and in the conclusion. So if I were to tell you that the conclusion is false, would that change your mind about whether the conclusion follows necessarily from the premises? It shouldn't really, right? It's the same as the previous cases. Okay, so I hope this set of three examples help you to have a better grasp of what we mean by the question, hey, is this conclusion a logical consequence of the premises? If it's not clear yet, don't worry. We're going to keep talking about that. And in fact, the next lecture will do a deep dive into that question. For now, let's move on to the second important methodological discovery of Aristotle. And this one is fairly simple, right? In the previous four cases of arguments in which we said that the conclusion necessarily follows from the premises, does it depend on whether we know that the conclusion is a logical consequence of the premises, or is there something like an objective fact about whether the conclusion follows from the premises? If, say, all of us ignored that a certain conclusion follows from the premises, would it stop following from the premises? No, right? So just like there are objective facts about the world, there are also objective facts about whether a conclusion logically follows from premises. Okay? So This is Aristotle's second deep insight, that there are objective facts about the connection between premises and a conclusion. And we're going to call this second insight of Aristotle knowledge independence. So the relation of logical consequence, which is really what studying logic is all about, it's objectively determined independently of whether people believe it or not. Okay, so that's a really important thing to meditate. You might not be fully convinced of that, by the way. That's okay. Hopefully, as we develop our set of patterns and techniques, you will see that those are objectively established and really not dependent on what we believe to be the case. Okay, now that we looked at the two fundamental methodological discoveries of Aristotle, without which he couldn't have invented logic, let's talk a little bit about two fundamental problems that we encounter when we are studying logic. The first is, like the first two examples about the islands that I was presenting you earlier, I give you a set of premises and I'm asking you, hey, find me a conclusion that logically follows from the premises. And this can be hard, right? Sometimes it's easy. Of course, I chose my examples earlier so that they would be easy because we're just getting started. Right? The second problem now is one in which you don't just have the premises and ask to find a conclusion that follows, but rather we're giving you the premises and the conclusion, and we're asking, does it actually follow? So that's like the third example about the islands that we saw earlier. Two different problems, two problems that are very important. And Aristotle's thought is that both questions depend on objective features of how we should use language, and that essentially factual matter about mortals, animals, the various islands we talked about, that doesn't matter at all. Right? What matters is pattern recognition. And this is why, again, we said logic is topic neutral. So in the previous lecture, I alluded to the fact that one of the challenging thing about logic, but also extremely rewarding, is that it's a very abstract discipline. And this is because of this topic neutrality of the rules of logic. They apply to everything, and therefore they are not articulated in terms of concrete examples. We really have to raise our level of abstraction to understand them. Okay? Now, the examples we saw earlier are fairly easy, but note that for both of those problems, often it's going to be extremely hard, right? And in order to become good at solving the hardest problems, we're going to need efficient logical techniques. And we're first going to use those techniques to solve easy problems. Problems really for which you wouldn't need those fancy mathematical techniques. In fact, they just seem to make things more complicated. But the idea is that you need those techniques for the hard problems, not for the easy ones, right? And well, we're going to practice them on simple problems and then ascend to a point where you actually need them to become good, reliable, and fast at answering the question, hey, is this conclusion following from the premises? All right. As I suggested, we use mathematical methods to do that because they provide a great generality. And I'm just going to give you a few insights here about how those mathematical methods are used in logic. Aristotle didn't use mathematical methods. He used something quite good, but it doesn't have the same generality that we can achieve when we're using mathematical methods. George Boole, that you might have heard of, is the person who introduced mathematical methods 2,000 years after Aristotle had invented logic. So it took a lot of time. I said some of you might have heard about George Boole. Probably if you were in computer science or took a programming course at some point in your life, you will have heard about those things that are called Boolean operators or Boolean tests. And that's in honor of the mathematization of logic by George Boole. In fact, those operators were developed 18 or 1900 years before Boole. So he didn't invent them, but he presented, he gave us the tools to mathematically understand how to deal with them. And his thought was that there is an analogy between answering the question, is this conclusion following from the premises, and solving mathematical equations. Now, today we don't really use the methods that Boole had developed. We have found much, much better methods. But the basic idea that doing logic is very similar to doing algebra has remained, and this is really what we're going to do in this course as we move ahead. Now, Boole's idea was worked very well for sentences like all animals are mortals or some mortals are not animals. You know, sentences that contain the word all and some, but only once, right? Those, by the way, those words, all and some, they're called quantifiers. There's two. We have to get our quantity straight. Yeah, so it worked well when there's just one quantifier, but he didn't have much to contribute to for cases in which there is more than one quantifier in a sentence. For example, here's one. Everyone loves someone who loves them. All right? That sentence has two quantifiers, one every and the other some. Right? And really, Boole's methods were not good enough to deal with those things. At least, I mean, it was convoluted. So it took 25 years only before someone introduced a method to deal with all sentences involving quantifiers. And compare that, right? From Aristotle to Boole, it took 2,000 years, and from Boole to the next person who is really important, only 25 years. And that person was Gottlob Frege, a German mathematician and philosopher. Often Frege is called the father of analytic philosophy, which is what is practiced in many of the North American English-speaking schools. So anyway, Frege introduced a very general mathematical language to understand sentences like that, and sentences that are even more complicated than that. And just to make you see the motivation, the scientific motivation behind what Frege did, let me just read you a quote that was in the introduction of his logical treatise, in which he introduced modern logic as we know it and as we'll study it. He said, I believe that I can best make the relation of my symbolic language to ordinary language clear if I compare it to that which the microscope has to the eye. Right? So ordinary language is just language in words, what we use, and the symbolic language is one in which we remove words and replace them by variables. That's the idea. And then, as I was saying, Frege introduced a general symbolic language to deal with all matters of logic, or almost many matters of logic. So let's continue. because of the range of its possible uses and the versatility with which it can adapt to the most diverse circumstances, the eye is far superior to the microscope. Right? The eye works for all sorts of situations, just like ordinary language works for all sorts of situations. But considered as an optical instrument, to be sure, it exhibits many imperfections, which ordinarily pass unnoticed only on account of its intimate connection with our mental life. But as soon as scientific goals demand great sharpness of resolution, the eye proves to be insufficient. The microscope, on the other hand, is perfectly suited to precisely such goal, but it is just why it is useless for all others. So the symbolic tools that we are going to develop to express our logical thoughts are also useless for conversation. The symbolic language we'll develop is not a language that anybody actually speaks. It's just a language that we use to clarify or make more precise our thoughts in order to have a greater sharpness of resolution as we need for the scientific goals that are associated with logic as science. I think that's a beautiful quote. Now, I said that Frege invented the symbolic language that is associated with modern logic. But in fact, he had a very cumbersome language. It had the right idea, and it did the right thing, and it had the right level of generality, but it was like a total nightmare to use. So in fact, in modern logic, we use tools that are a little bit closer to what two persons introduced, David Hilbert and Bertrand Russell. David Hilbert was the greatest mathematician in the world for about 20 years at the beginning of the 20th century, and also an extremely sharp philosopher and logician, one of my favorite. I wrote my master's thesis in philosophy on Frege and Hilbert. And the second one is Bertrand Russell, who is, well, one of the most famous philosophers, if not the most philosopher of the 20th century, also a winner of a Nobel Prize in literature, of all things. In any case, I'm not going to talk much about those people. I just wanted to flag their importance. And two other people who are very important are Kurt Gödel and Alfred Tarski. If you were to take a more advanced logic course, those would be two important figures. Or perhaps you will have seen them in a course, or you will see them in a course in computer science or something like that. I don't want to talk about Tarski, but I just want to say something about Gödel. By the way, Godel almost immigrated from Germany for obvious reasons when a certain party with a guy with a little mustache took power in Germany. He immigrated to the US, and he almost failed his citizenship exam because he was trying to argue that he found a way to legally establish a tyranny in the United States. And apparently he was stopped from talking too much, so eventually they did give him his citizenship. Godel also was the first to prove that according to the general theory of relativity, time travel is possible. So yes, we know it is, in theory, at least. But now I just want to mention one incredible idea that Godel had in the domain of logic. And he had many. But Hilbert, the guy I mentioned earlier, the great mathematician, was also an incredible optimist about our ability as humans to solve any problem that could be presented to us. And here's a quote from him. He says, "We must not believe those who today, with philosophical bearing and deliberative tone, prophesy the fall of culture and accept the ignorabimus." The ignorabimus meaning the existence of things that we ignore and will always ignore. And he says, for us, there is no ignorabimus. And in my opinion, none was ever in natural science. In opposition to the fooling ignorabimus, our slogan shall be, we must know, we shall, sorry, I thought it was we shall know. Anyway, different translation. We must know, we will know. Well, very, very optimistic about what science can achieve. But then the question that arises, well, is it just a matter of opinion or a matter of values, about whether we are optimistic or pessimistic about the reach of science? And I think a very natural stance is to think, what else could it be, right? And Gödel's thought was, well, no, I think we can prove which of the two stances is correct. And in fact, that's precisely what he did in a famous paper in 1931, if I remember well. And I think this theorem proves the incredible and spectacular power and subtlety, and sorry, I said subtlety twice, and beauty of logic. And Gödel proved mathematically that Hilbert was wrong. And in order to do so, he had to make incredible developments in logic that you would study in an upper year course. We're not going to do that today. I just want to tell you how cool it can get at the higher level. But he proved that Hilbert was wrong and that there necessarily are things we couldn't know in mathematics and also in natural science. Isn't that remarkable that this thing that seems just to be a matter of opinion, in fact, is susceptible of receiving a definite proof using logical tools? I think that's absolutely amazing. Now, in case you're interested in learning more about that, that's called Gödel's incompleteness theorem. You can Google it. You're going to find information about it. We would talk about that in an upper year course and in some upper year courses, but not in this course because it belongs to a part of logic that's called meta theory, and we're not going to study that systematically in this course, which means that we cannot explain Gödel's argument in details, but just having an idea of how cool logic can get, I think, is valuable. Now, you may have noticed that all the dates I was giving you were from the beginning of the 20th century, and you might be wondering, is there still any progress in logic? And there is more progress in logic now than there's ever been. But I just want to mention some famous names, people who have received important prizes. So now we're going to talk about, say, between 1940 and say, 1980. Of course, there is still a lot after that, but one is Julia Robinson, who made massive contributions to the foundations of mathematics and computer science by her work on solvability of equations, among other things. Then there is someone called Ruth Barkin, and another person, I don't have her photo here, but it's Angelika Kratzer. Angelika Kratzer is still active and amazingly good. And basically, they made huge contributions to a field of logic, which is about studying modalities. Modalities are things like possibility and necessity, and permissibility and obligations and all sorts of things like that. So they contributed to our understanding of modalities both in logic and linguistics and cognitive science and computer science. Very important work. And then there is a work by Noam Chomsky, Richard Montague, and Barbara Party, who is here. That's really made huge contributions to formalize our understanding of how language works, that eventually made it possible to develop things like computer-assisted text recognition and things like that. Again, today we don't use exactly those methods. There keeps being progress, but they were massive pioneers who used the tools of logic to enable a much deeper understanding of how language works. Yes, so Chomsky was a logic buff before being a political activist and a political scientist. All right, so that's it for this little historical snippet. I know it was a little bit in all directions, but I just wanted to give you an appetite for logic, and I hope it's worked. So now let's come back to something a little bit drier, which is just looking at some of the basic words that we're going to use all the time when we are going to do logic. So I just want to go over them to make sure we're all on the same page. So those words are argument, inference, statement, proposition, premise, conclusion. And we're going to try to understand them rigorously. We all have an understanding of those words at some more or less precise level, but now we're going to say, hey, in this course, when we use that word, that's what we mean exactly. So let's start with sentences, statements, and propositions. And I like to do Venn diagrams. So let's think of a written language, right? A written language has an alphabet. In English, we have 26 letters. We also have numerals and various other symbols, punctuations, and whatnot. And then we can form strings of characters or strings of letters, if you prefer. And some strings are meaningless, and other strings form words, right? So once we have determined which strings of letters form words, we can also combine those strings of letters, those words. And again, some combinations of words are complete nonsense. They are meaningless. But other sequences of words do make sense. And some of the sequences of words that make sense are sentences. And again, I don't want to go into details because that would get us into, relatively complex grammatical thinking, but I don't think we need it for this course. So this is why we're going to sidestep all of that. All that matters for us is that some sequences of words are sentences and some aren't, right? So sentences also come in different types. And you're all familiar with that, but let's just look at a few examples. So one type of sentence is questions. Who's going to win the curling championship? Canadian content. We're talking about curling here. Right? That's a question, right? Good old question. Then you can have a request or a plea or even an order, right? Please don't tell anybody I like watching curling on TV. Some people are ashamed to admit it. I say it proudly. I love watching curling on TV. Again, commands. If you watch curling on TV, you will have heard that one a lot. Come on, sweep, 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 and things like that. Exclamations. Oh, what a beautiful stone placement. That's what the commentator would say, probably, when the Canadian team has just played. And of course, there are many, many other types of sentence. What I'm trying to get to here is that in logic, we're not interested with all sentences, but just with one particular type of sentences. And it's not one that is among the four that I've just mentioned. Rather, it's what is called a statement. And again, just to flag something, if some of you are in linguistics, there are two different meanings of statements. One of them is the one we're going to use here, but the other isn't, so just be aware of that. For the others of you who have no idea what this ambiguity is, ignore it, right? So here we're going to mean by statement a particular type of sentence, and here's an example. Canada wins most gold medals in curling at the Olympic Games, right? Now, what distinguishes this type of sentences from the other ones, right? Well, is that the last one, it makes sense to ask if it's true or false. But for the other kinds of sentences, it does not make sense to ask whether they are true or false. I suppose someone says, who's going to win the curling championship? True or false? You're like, what are you talking about? That doesn't make sense to ask if that sentence is true or false. However, it does make sense to ask that of the last type of sentences, namely statements. And this is why in logic, we're going to be concerned with statements only. And again, little asterisks. Some branches of logic that are more advanced also consider other types of sentences. But anyway, for this course, for elementary logic, statements are the only ones that matter. So what is a statement? Well, as I said, it's a sentence for which it makes sense to ask if it's true or false, or to say that a little bit more precisely. A statement is a sentence or a part of a sentence that expresses something that is either true or false. Another way of putting it that makes clear why it's called a statement is to say that a statement is a sentence or part of a sentence that states a fact. Doesn't mean that the fact is true, but it does state one, okay? So that's what a statement is, a particular type of sentence with that property. Another intuitive way of figuring out if something is a statement or not is to ask, suppose someone utters that statement or makes that statement. It makes sense to ask, hey, did that person tell something false or did they lie, right? If it's not possible to lie by uttering that, then probably it's not a statement. It's a general idea. Not a perfect one, but a sort of rule of thumb. So then we see that all statements are sentences, but only some of the sentences are statements. So let's do a little example here. Are they sentences? Are they statements? Let's look at the first one. 1 is the smallest prime number. Is that a sentence? Yeah, it's a sentence. It's a complete grammatical unit. All right? Is it a statement? Yeah, it does state a fact. Now, is it true? Is 1 the smallest prime number? You might be thinking yes, but the answer is no. So Google it. Second one, let's go Canucks. Is that a sentence? Yeah, it's a sentence. Is it a statement? Well, not really, right? It doesn't make sense to ask if it's true or false. What about the third one? God exists. Is it a sentence? Yeah, it is. Is it a statement? Now, some of you might be agnostic here and you're like, well, we don't know what the matter of fact is, right? But really, to be a statement, it doesn't matter whether we know if it's true or false. All that's required is that it's either true or false, and certainly that qualifies for this sentence. So the third one is also a statement. Next one. Did I mention that I hate the Montreal Canadiens? Well, I didn't mention it, but I do. I really, really hate them, which you might find surprising. But that's because I'm a fan of the Nordiques, a team that existed before most of you were born, and I'm just waiting for their return. Now, anyway, that's a sentence, but it's not a statement. It's a question. Next one. In North America, football is a sport played mostly with the hands. Yeah, the name works. So that's a sentence, and it's also a statement. It asserts a fact, it expresses a fact, and it is in fact true. Now, the last one is a little bit trickier because it is a sentence. I wish it were cooler outside. And for some reason, I'm not exactly clear about. Some people argue it's not a statement, but to me, it seems like a statement. It just expresses something about my wishes. So I just want to flag that some people have debates about what constitutes a statement or not. They are in ordinary language. There are clear cases of statements. There are clear cases of things that are not statements. And in the middle, there are some that are a little bit more difficult, right? And there are true debates about that. In this course, I'm just going to give you examples that are clearly a statement or clearly not a statement. Okay. Now, note that even if a sentence is not a statement, it can contain a statement. And let's revisit one of the examples that we just looked at. Did I mention that I hate the Montreal Canadiens? As we saw, this is not a statement because it's a question, different type of sentence. On the other hand, it contains I hate the Montreal Canadiens, and this is definitely a statement, right? It asserts a fact, and believe me, it is a fact. I do hate them, right? So we have here a situation where we have a sentence. That sentence is not a statement, but a part of that sentence is a statement, right? Some statements also have parts that are statements. We're going to study that a lot in the next few weeks. All right, so I hope so far everything is clear. I'm sorry I'm a little bit over time. I should have perhaps been a little bit faster. So my apologies. Fortunately, it's pre-recorded, so I'll keep going. Otherwise, the next one will be longer, so it's all even here. So now we can complete this picture, our little Venn diagram, by putting the statements in the middle. And this little green part in the middle of our Venn diagram is really what we're going to be studying in logic. So everything is clear now, right? But yeah, there are still a few things that we ought to clarify, because I talked about sentences, I talked about statements, but I didn't talk about propositions yet. And that's important. So what's the difference between a statement and a proposition, right? The idea is that a proposition is a sort of abstract entity, namely the meaning which is expressed by a statement. And different statements can express the same proposition, and propositions correspond to the meaning of a statement. So let's just look at some examples, and hopefully it's going to be all clear. I'm not going to talk too much about propositions because for this course it's not essential. I just want to flag the difference. So suppose I say a truck has run over Joe, and Joe has been ran over by a truck. Are those two sentences expressing the same thing? Do they have the same meaning? And then it seems like they do, right? One is in the active voice, the other is in the passive voice, but we have switched the subject and the complement. So yeah, those two sentences are expressing the same proposition. Here's another one from one of my favorite martial arts movie actor. Jackie Chan demonstrated the Zhuai Chuan, sorry if I butcher it, fighting style in one of his early movies produced in Hong Kong. In one of Jackie Chan's early Hong Kong movie production, he demonstrated the fighting style known as Zhuai Chuan. So again, we have two sentences where the words are organized differently. There are some grammatical distinctions, but they say exactly the same thing, right? So two sentences here that express the same proposition. And the last example, snow is white and la neige est blanche. You might not know French, but trust me, the second sentence says the same as the first one. And so you can have statements in different languages that also express the same proposition. And if that weren't the case, then it would be impossible to translate things from one language to the other. So we're lucky that this is the case. Okay, just one last set of terms, and then we're going to close that. So inferences and arguments. So Note that if you're using the first edition of the book, they define them differently than they are now defined. I think the new one is much clearer. So an inference is basically an operation of our mind, something that we do with our brain. And it's passing from a series of statements to another statement that we seek to establish by virtue of the first few statements, the series of statements we start from. Now, the statement we wish to establish is called a conclusion, and the series of statements we start from, those that provide the support for the conclusion, are called the premises. Okay? So this is why we say the premises, in a good argument, the premises lend support to the conclusion. Now, most of the time, perhaps, the premises and the conclusion are all in different sentences, but sometimes they aren't. They are components of a more complicated sentence. So let me just give you an example. Suppose I say, it will not rain this afternoon since there are no clouds in the sky. Okay? Now that's an argument with one premise and one conclusion, right? That sentence has two component statements, one acting as the premise. Here, there are no clouds in the sky, is the fact we start from. And then, it will not rain this afternoon is the one we want to lend support to by saying that there are no clouds in the sky. Okay? So, here we have an argument, all expressed in one sentence. Now, sometimes there are a bunch of statements that are not arguments, right? So an argument is a very special way of putting a bunch of statements together. Other kinds of bunch of statements are descriptions or narrations and things like that. The question is, are they connected logically? So if they are presented so that some of them are meant to lend support to another one, the conclusion, then we have an argument. Otherwise, it's a different bunch of statements, not an argument. Examples. Justin Trudeau is the Prime Minister of Canada. By the way, he's also the king of the selfie. Less true today, but he used to do a lot of selfies. Now, the word by the way indicates that those are two disconnected thoughts, right? So here we don't have an argument. It's just two independent statements next to each other. Now, suppose I say, once upon a time, Snow White was sleeping in a house, then 7 dwarves arrived and started goofing around. Now, very often the word then is in fact going to indicate a logical connection. But here it's just indicating a sort of temporal order. So it's just a narration of a number of events, and there isn't really one or more statements providing support or lending support for another one. Here's another one, longer. Cats always land on their feet. Toast with jam always land on the side with jam. Therefore, a cat with a toast with jam strapped to its back couldn't fall either side and would levitate forever. So pause for a second and try to visualize that in your head. I think that's amusing. Now, here we do have an argument, a kind of silly argument, but it's still an argument, because the word therefore indicates that the first two statements are meant to lend support to the third one. Now, whether they actually lend support is a different matter, but at least they intend to lend support, and that's enough to make it an argument. Okay? So we can formalize what we just said by saying an argument is a collection of one or more inference seeking to establish a main conclusion. So an argument is a big thing containing one or more inference. And if there is more than one inference in the argument, then the conclusion of the particular inferences are going to be called sub-conclusions. Now, are there good ways of identifying inferences and how they are connected with each other to generate complex arguments? Then the answer is yes. They are called premises and conclusion indicator. And we're going to look at them next time. So make sure that you look at chapter 1, and there are 3 subsections that you can omit because we're not going to touch them and they're not that important. So have a look at that, and then we're going to start next time with premises and inference indicators. So see you next time.